Welcome to this session about polymorphic table functions. The subtitle is the best way to integrate SQL and Spark, and of course you probably know Spark SQL, but that's not the focus of this presentation today. What I will be talking about is if you have some kind of data store which has a SQL interface, and how to integrate with Spark from that data store. Now let's look at what we will be talking about today. First, I will try to give you some motivation why I am talking about polymorphic table function. What's the traditional way of integrating Spark and SQL? You probably know that. And then I will talk a bit about the problems with this approach and how polymorphic table functions can solve that, or what's different with the approach with polymorphic table functions. Then the main part of this presentation will be about polymorphic table functions. What are they? How do they work? And I will also show you some use cases for polymorphic table functions. And finally, I will just summarize. Okay. Let's look how the integration of Spark and SQL is usually done. Usually, the action comes from Spark itself. Spark needs some data for processing. Therefore, it reads data from a data store and writes the results, which are computed again to a data store. And of course, there are many options what to do using JDBC, accessing Parquet files, whatever. There are a lot of options in Spark for doing that. But the general principle of that approach is that Spark is in the driver's seat. That's not what you always want to do. Sometimes you want to take the data store, the initiative, and that the data store can use Spark for doing some computations on a table, for doing some transformations or something like that. And especially if you want to do some complex transformation on data in your database, which are too complicated for SQL, or might be they are possible with SQL, but it's much easier to do them in something like Spark. And therefore, there is a need for having integration between Spark and the data store with the initiative coming from the data store. And the solution for that are the polymorphic table functions. Okay, let's look at what polymorphic table functions are. Polymorphic table functions are, as the name implies, table functions. And these table functions, in this specific case, because we want to integrate with Spark, are calling or executing Spark code. And well, if you are not familiar with table functions in SQL, there are functions which present the result of their computation to Spark, to SQL as a table, as a relational table. And therefore, you can use a table function in the from clause of your SQL statement, just any regular table. You can do joins on that. You can do the joins with other table functions or with regular tables. You can do filtering, grouping, whatever on these tables. But why are they called polymorphic table functions? Well, usually a function has a specific signature. It is returning a table of a specific type. In the case of the polymorphic table function for executing the Spark code, there will be one table function which can return many different tables. They can have different numbers of columns, different types of columns, and therefore, because there's just one function which can have many shapes, therefore it's called a polymorphic table function. In this presentation, I will use an example of a specific polymorphic table function, which is used in Big SQL. And I will talk a bit about Big SQL later. If you are not familiar with Big SQL, just accept at the moment that it's some SQL engine mostly used in a Hadoop environment. And there's a polymorphic table function which is called execspark. And when you're calling that table function, then you have to pass a class as argument, and this class implements the Spark PTF like polymorphic table function interface. And this class must be written in Scala or Java, and it must implement 4 methods. One method is the describe method, which is used by Big SQL for, well, understanding the format of the table. Describe gives the columns and the type of the columns back to the SQL engine. That's for the optimizer before the query is running. When the query is running, of course, there has an implementation which really executes that, and that's a method execute. And well, there are 2 additional methods. One is the destroy method, which is just called for cleanup after the polymorphic table function has finished. And in addition, there's a method cardinality, which gives a hint to the optimizer how many rows to expect, because for getting the best query plan, optimizer usually has to know something about the table which is using it, and the minimal kind of statistics is usually the number of rows which are in a table. Okay, what I want to give you next is a complete example of the usage of a polymorphic table function and of its implementation. It's a really simple example, just the reading of a JSON file and presenting the JSON file as like it would be a relational table in Big SQL. And here on this slide, you see how the polymorphic table function is called. As we have seen on the previous slide, it's called execspark. It's in the schema sys Hadoop. And we are using it in a from clause, like one would use usually a table function. And we are passing in a class which is implementing this functionality to read a JSON file. We will look at that next. And we are giving an additional argument, URI, which is the file which we want to present as a table. That's the call of the polymorphic table function. And around that, we see that we can use it just, well, like a regular table in SQL. we are doing some filtering in the where clause here. We are doing some order by. And of course, we are just projecting one column from that table. Next, let's look at the source code of the implementation of the class. There are some imports. I think the last line is the most important one, where we are importing Spark PTF. Next, let's look at the describe method. You see the class definition that it implements Spark PTF, and we are defining a data set df, which we use for representing the table. And what we are doing in the describe function, and we see that we have two arguments. We get a SQL context CTX, and we have a map arguments. The arguments are the arguments we just passed to that call of the polymorphic table function. And what we are doing here, that's very easy to implement because most of that is already available, and we just have to give the argument URI. We extract that from arguments and pass it to read JSON and store that in df. And then we just do df.schema for getting all the information about the columns and the types. Therefore, I have chosen that example of reading a JSON file because that's very short to implement, and we can see the complete example in this presentation. The next important method we have to implement is the execute method. You remember that's the one which is doing the actual work and returns the table. And here we again read the JSON file, which is passed with the argument URI, if you haven't done that yet. If we have done that, then we don't have to do it. We just return df in that case. Therefore, df is the vehicle for parsing the JSON file and converting it to a table. And now let's look at the two remaining methods which we have to implement. Well, the destroy method is very simple. It just sets df to 0 if it isn't still 0. And the cardinality method is also very simply implemented. It's looking whether there is an argument card for cardinality. And if that argument is passed, then, well, we just return that. And otherwise, we return a constant 100. That's our best guess in that case. Therefore, we have the possibility, if we know how big the JSON file is, we return that. Of course, for a real implementation, one would usually do a much better implementation for cardinality. But as I said, it's just used by the optimizer for finding the best query plan. Okay, this was a very quick overview how polymorphic table functions work. Now I want to talk a bit about what Big SQL is and how Big SQL is integrated with Spark, because there's a very efficient communication for that. Big SQL is a SQL engine which has, well, all the functionality in your SQL which you usually expect from a relational database. But it's targeted for Hadoop environments, or you can use it also if your data is stored in Cloud Object Storage. And besides being able to process in parallel large files in a Hadoop environment or in Cloud Object Storage, there are several other aspects. It is very fast, much faster than most other SQL engines, especially the default engines which you usually have. It is very scalable. It has a compatibility to several relational databases. There's a compatibility to Oracle, to DB2, to Postgres. And another specialty of BigSQL is the data virtualization, which it offers. This means that you have the possibility to access data in a lot of different data stores outside of BigSQL and also present them like tables, and of course to join these remote tables with something like your polymorphic table functions. And it is using the Hive Metastore, and it can also access data in a HBase database. Therefore, it's having a lot of compatibilities. And there's bidirectional integration with Spark. Of course, you can talk to BigSQL in the traditional way from Spark. You can access data in BigSQL from Spark, but it has also the polymorphic table functions, which we are talking about in this presentation. This slide just visualizes a bit. At the top, you see all the data sources which you can virtualize in a BigSQL. Virtualize meaning that you present tables in these databases like a table locally in BigSQL. And that's not just for relational sources, but you can do also that for NoSQL data stores. And you also see there are a lot of options where your data can be stored. And here you see how BigSQL and Spark are communicating. And the main aspect of that is that there is a long-running Spark app which allows for very fast communication with low latency between Spark and BigSQL, because Spark doesn't have to be started for each request, for each polymorphic table functions or something like that. It's already running there. And therefore, Spark can also be used, for instance, for caching tables in memory for BigSQL, something like that. And the other important thing is that both Spark and BigSQL are scalable engines which can be running in a large cluster, and they are collocated. For each BigSQL worker, there's on the same node a local Spark executor, and also for the BigSQL head node, the Spark driver is running on that node. And therefore, there's very efficient communication. In many cases, you avoid transferring data via the network, and usually the network is the most expensive resource that you have. Okay, let's look a bit more in detail how BigSQL and Spark are communicating. Let's assume we have some SQL statement, like the SQL statement which we saw before in the example, where exec Spark is called with some class. that's submitted against Big SQL, this SQL statement. And Big SQL is calling for the polymorphic table function the describe method of that. And in the Spark driver, of course, you have a local storage of your class, and then you are reading, for instance, in the case of the JSON file, you are reading the JSON file, and you are returning the schema, or whatever your describe method is doing. It's giving the information about the schema to Big SQL. Big SQL is next starting the computation on the Big SQL worker nodes and executing or calling execute in Spark. And Spark is initiating the computation on all the worker nodes. That is going on. And then when the computation is done, Spark is transferring the result locally on each Spark executed to the corresponding Big SQL worker. Therefore, that's a very efficient way of communicating with a very low latency. Here you are seeing how this is just summarized. You are having parallelism. You have local communication. There is streaming from the data frame in Spark to Big SQL. And therefore, you have a very efficient and fast communication. Now, what are use cases for that? I told you that there are a lot of data virtualization capabilities in Big SQL. But of course, there are data sources which are not yet available for Big SQL, and you can implement them as polymorphic table functions. And sometimes it's very simple to do that because in Spark SQL, there is already a data source available for that. And you can use that to virtualize that as a table in a Big SQL. I mentioned in the beginning that you can do very complex transformations with your Spark computation, usually more complex than what you can be doing in SQL. And this can be, for instance, used for something like ETL, for transforming tables. But you can also use, there are a lot of machine learning libraries available in Spark. And if you want to bring your computation, your machine learning directly to the data, if you have a large amount of data, then this is very efficiently done with polymorphic table functions. Another use case is if you want to do custom aggregates. Again, might be something which is difficult to express in SQL, at least for many SQL dialects. And this can also be done with something like polymorphic table functions. You are passing the table which you want to aggregate to Spark, and Spark is doing the aggregation and is returning the aggregated table. Okay, let's just look at a few code examples. Here you see an example how to, well, virtualize my SQL table in Big SQL with polymorphic table functions. Next, we see how you can do that for CSV files. Again, just using the data source in Spark for doing that. And the last one is how to do that for Parquet files. And for all these examples, you are seeing that you're using where clauses or whatever. Because, for instance, age is something which is a column in your Parquet file, and you're just checking that, and that's what you can do with polymorphic table functions. And just to summarize, what are the main functionalities which are enabled with polymorphic table functions? It's a way for fast and scalable communication and transfer of data between Spark and the SQL engine. The example which I gave you was for the big SQL engine. In the naive implementation, which I gave you in the beginning, or which I called also the traditional implementation, you have to have an intermediate storage when you're transferring the data. That's not necessary. You can directly transfer data from memory to memory with polymorphic table functions. And we saw that there are many use cases possible, and you can think yourself what might be a possible use case in your environment. And all the analytical capabilities in Spark are now also available in the SQL engine, which is using the polymorphic table functions. And with that, I just want to tell you that's my contact data. If you have any further questions, send me an email, follow me on Twitter, whatever. Thanks.